So I think we'd like to start off by thanking everybody for coming today. I think we're very excited to share some of the work we've been doing on ATD2. As Al had mentioned in kind of our kickoff this morning, this is really the room for the quote-unquote data nuts. So you're going to see a lot of data here. We'll start off by kind of showing how we extract some of the raw data elements, and that is what Andrew will talk about here over the next 2 sessions. And then after we talk about how we extract the data, we'll talk a little bit more about what we do with the data once we have it in our hands. To introduce myself, I'm Jeremy Koop. I'm the ATD2 analytics lead. I've been working on surface systems going back to about 2012, where I worked on the precursor to the ATD2 system called NASA's Spot and Runway Departure Advisor. So been working on the surface for quite a long time. Throughout the analytics track, you'll see me either up here at the podium introducing our speakers or also giving some of the talks. But to begin with, the talk this morning will be given by Dr. Andrew Churchill. And I think he has a pretty interesting talk here to share how we kind of get some of these data into a consistent product that our analysts can work with. And that solves a lot of problems for us in terms of having a consistent view of the data before then you go and make these more kind of complicated data products. And so without any further ado, we'll pass it off to Andrew and he'll get us started here.
All right, thanks. So I hope it's an interesting presentation, as Jeremy promised you. We'll see. Some of you may have seen some variation of this at some point, but there is quite a bit of new material in here. So if some of it looks familiar, just wait. We'll get to some new stuff. So the title here, SwimFuse Data Products Used by ATD2 Analysts for Quantifying NAS Performance and Benefits. So I think that Al came up with that title. Maybe not the one I would have used. It's a lot of words. But what we're really talking about here is reporting. And sort of reporting in the business intelligence context, on the sort of traditional analytics maturity curve, before you get to predictive and prescriptive analytics and the exciting data science stuff that people were referencing in the opening session, you have to have a good understanding of what data you actually have and a clean sort of uniform representation of that. And that's sort of reporting. And that's really what we're talking about here. This is sort of the foundation for the analysis efforts that we're doing on the project. So we're going to talk about in this first session this morning before lunch about the sort of flight level data that we generate and use across the project. And this next session after lunch, we're going to talk about some other data reports that we generate and use looking at TMIs and TOS for the phase 3 section of the ATD2. So like I said, we're talking about the flight summary report here. That's just our internal name. I guess it's not totally internal now. The data is shared with some partners. Our name for our flight-specific data set that's it's grown pretty large. We talk about the different kinds of data elements that are in there and how we compute those and sort of our philosophy underlying the whole thing. Lots of questions and answers, so do feel free to raise your hand if you have a pressing question as we go along. I don't want anyone to get lost. We're using the conference I/O system as well, so feel free to put in there and vote, and we'll keep an eye on those and make sure we're addressing things. So however you want to participate, feel free. And we'll also reserve some time at the end for questions and discussion. So we're in session 1 here about sort of ATD2 reporting. So some background and sort of our overall philosophy here. The ATD2 systems, there's multiple of them now. Charlotte obviously has a lot of interest as the TFDM precursor, but there is a big system running for DFW and some other sort of back-end systems that are involved here. So there's a lot of infrastructure that's ingesting a huge amount of swim data. We're not going to talk about necessarily how that raw swim data gets into something the system uses here in this session, but there is content out there about this data fusion process. So we're working with this fused data on this side, and we have this very large set of data that the system does something with, and then the ATD2 system outputs this huge amount of data, recording basically every aspect you could imagine in the operation. In terms of tabular data, but also in terms of video and all sorts of other things. So there's a huge amount of output. It creates a huge sort of scale problem if you're an analyst trying to work with this data. So part of the problem we're trying to solve with this reporting work and the sort of roll-ups that we're generating is to abstract away some of the scale that can be challenging for some of the analysts to use and can also be challenging from a computational perspective, that we don't want people to have to take minutes and hours to answer simple questions. We want to sort of solve that ahead of time. So we have a scale problem we're trying to address. I mean, there's literally billions of rows in these databases. So besides scale, I've sort of grouped some other issues we're trying to solve in terms of noise here. So things like human inputs. There are inputs from ramp controllers and controllers in the tower, and sometimes they hit the wrong button or the wrong flight. They undo things. There's just some sort of human interaction in the system always can generate some potential ambiguities, and we need to make sure those are properly accounted for, and not necessarily have to rely on every analyst knowing the right way to account for all the different kinds of things that could emerge there. Complexities of the data mediation, so this data fusion process, all the different swim feeds and airline feeds that are being joined in the ATD2 system, sometimes that creates some complexities, it's another way to describe it really, in how we use the data. So the data that's then available for an analyst, we don't want them to have to deal with understanding and knowing intimately the details of what's going on there. Order of processing messages, I mean, there's so many messages flowing through here that creates some challenges, which system sort of stepped on top of the other one. As the ATD2 software has evolved, there's been some changes in sort of how some data are recorded, which data are recorded. So we're trying to create a consistent view over the life of the project of what the operation looked like on every day for every flight. And so if we start recording some data element halfway through, we want to think about, is there a way we can infer that from the old data that we have? Is there some way that we can make sure the analysts get a consistent view, longitudinal view, throughout the project to try to be able to generate, a lot of these questions we can only answer with some time. So the more time worth of data we can make available, the more questions we can answer with more confidence. So we have sort of standard conventions, as one does. I mean, this is not unique to ATD2. Every enterprise has sort of standard conventions for how they handle data, how they record things, how they measure things. So we need to implement those without having to sort of force that extra work on every analyst on the project. And there's a pretty big team of analysts working on the project between NASA and contractors. So there's a lot of people. There would be a lot of difficulty in expecting everyone to handle that. So we're trying to, again, extract away as many of these problems as we can. So we've developed these standardized reports, summary files that serve analysts and user needs. So we're going to talk mostly about the reports, the summary files themselves that are generated each day describing the operation. Those summary files are then turned into reports in sort of the traditional business intelligence context that are shared with users to provide common situational awareness. So we'll talk about some of those at the end, but and obviously there's specific questions or people want more details on what those are and how they could learn from that or use it in the future. We can talk more about that. So the core data files, the 3 core data files that are generated from the ATD2 data for analysis and reporting. The flight summary report, as I said, that's what we're going to talk about here. It's a tabular report. It's a file you can open in Excel, but you can load 1,000 of them together in sort of more robust statistical analysis software. Generated each day. There's 1 row per flight. So we try to the fuser groups all these pieces of data into one unique flight, and then there's many rows for that flight in the database. We're trying to roll up all those rows for that one flight into 1 row in our output file to summarize what was really the life cycle of that flight. And have some added value metrics as well. So in the session after lunch, I'm going to talk about the second and third ones on here, the TMI summary report, just talking about the traffic management initiatives and the parameters of those. Some really important questions. We can answer those from a program level rather than from a flight level, because we have some of that same data available in the flight summary report. And then the TOS summary report. This is our latest piece of work, talking about the trajectory option set concept that's being used, explored here in the North Texas region, and how we want to summarize that data to do analysis and answer questions about trade-offs and delay and routes and all these things. So we're going to start flight summary though. We're going to talk about that for a while in here. Again, any questions as we go through, please feel free to stop me.
How do you define flight from wheel up to wheel down? Or do you include anything that has like a technical stop?
Yeah, that's a good question. So yeah, it's landing takeoff operation. So and really dealing with one airport at a time, it's really either a landing or a takeoff. So we do get into some complications if there's a diversion or a return to the airport or a return to the gate. Those can create some challenges for the system, but we try to incorporate that kind of logic. But it's really just sort of one, push back to takeoff or landing to gate in with some near airport off the ground stuff. Generally, the system will create a new, we'll capture that as a flight, and then the system itself, upstream of the reporting, will create a new flight there when that aircraft is again ready to operate again. Yeah.
I want to make sure I have this right. Your definition of a flight is the one that's on the ground that is turning. It's not the flight that is taking off the landing. What is your definition of a flight?
Well, so a departure for us, we receive pre-departure information, obviously. The departure operation sort of starts at Charlotte, for example, when the pilot calls ready or when we get a pushback message.
So you're doing it from departure to arrival, you weren't talking about turns. Okay, I just wanted
Yeah, no, we do track turns. There is information being tracked in the back end about turns. So we're looking at aircraft connections and gate conflicts, but that's not really what we're rolling in here necessarily. Good question, yeah, because the scope is really important. I mean, when we try to answer these analysis questions, we want to make sure we're being precise. So from a technical point of view, very quickly, how we're doing this. We have these massive data warehouses, these big servers. They're actually located here in Dallas. That each morning we take the data from the operational systems at Charlotte and DFW. We treat a day as 4 a.m. local to 4 a.m. local, sort of trying to find a point in time when the airport is very quiet, so we don't have flights rolling over from one day to another. So we run this big script that takes 15 to 20 minutes, depending on the load on the server. It's written in Python. It runs a bunch of SQL queries, so running against the database, asking all these questions and combining all the results into this big table. There's a lot of different ways you could do that. That's sort of the way the technical approach we've developed. It works for us, but there's a lot of ways, going forward. Others could implement a similar approach. But the key point here is really the picture that we've got there. These tables that have all this flight data, that have a flight state, if you will, and the chain to the deltas at every instant, they end up with these very long tables. What we're trying to do is turn those very long tables into much shorter tables with 1 row per flight. That's really the goal of what we're trying to do here. All the scripts and the queries are compatible with all the AT2 airports. All the systems we've stood up are able to work with the same code base. So, it ends up a little funny sometimes when we have these TOS-related columns for the Charlotte reports, but the point is that everything is cross-compatible. So we just end up with a lot of empty columns, if you will. But we're trying to sort of maintain compatibility and not have distinct approaches by facility. So here is a laundry list of the modules, if you will, some of the groups of columns that we generate and that appear in this report. So I will just read through these real briefly, and we'll go through and talk in sort of more detail about what's in scope for each of these and what we're trying to do and some of the assumptions and math behind them. We start off with things like basic data. When was a flight scheduled to take off? When did it actually take off? When did it schedule to land? When did it actually land? What gate did it use? We look at things around banks. Obviously, Charlotte and DFW have a pretty strongly banked schedule, so we're trying to capture some notion of that. Ramp controller clearances, obviously of great interest at Charlotte. Flight states, some way the system is modeling the flight in the back end. Surface metering, we have a whole suite of metrics we compute there, for Charlotte. Times and locations predicted at events, so the ATD2, the underlying engine in the ATD2 system is making predictions continuously, and we're trying to sample some of those predictions to be able to look at the accuracy. EOBTs, L times, and sort of the accuracy of those metrics, very important data element for us, so we're trying to, roll that up in a way we can look at it over time. TMI impacts, so we have flight-specific TMI impacts that we look at in this context from the flight direction. We also have a different report I'll talk about after lunch, so we look at from the overall program level, what was the rate specified for this TMI and what were the start and stop times. Taxi times, a very interesting piece of the system. We're able to measure actual taxi times and segment that by ramp and movement area, but also we have estimates for the undelayed taxi times. Gate conflicts, that came up a couple times in the opening session. A huge issue with service metering. We're able to, we have modeling of that in the back end, and we do some reporting on how severe a gate conflict was for any specific flight. Pushback times, I'll talk about how many different kinds of pushback times we know about and why we're interested in those. Airport configuration, that's something that changes at the airport level through time, but we want to know for each flight what was the configuration that was going on when that flight hit specific milestones. Downline times, when did this flight eventually arrive at its destination? And Jeremy will use that. We'll show a presentation later that uses that data to say, is ATD2 causing any harm to sort of downline performance when we're metering in Charlotte? On-time performance for the local facility, how is that changing? What does that look like over time? And there's some complexities there. Again, some of these things may sound very trivial, but when you really get into the details, there's some significant complexity that exists with these. AEFS, so that's the electronic flight strip system that ATD2 integrates with. We have some visibility into the data there we roll up. We try to incorporate some surveillance data. Obviously, surveillance data is very verbose, right? I mean, the ASDX system is giving a hit for every aircraft every second. So we got to find a way to sort of summarize that in a useful way. And then we do have some flight-specific TOS-related data that we'll talk about that's put in here.
I would just like to add one thing. So Andrew did a really good job kind of laying out a lot of the data elements we have available. And we talk a lot about the fact that ATD2 is a precursor to TFDM. But one thing to keep in mind, we have additional data elements that were not in the TFDM requirements. And we found them very useful, and those are some of the things we're trying to pass on as lessons learned. For example, we capture what's called the pilot ready time, which is not a data element that would be in TFDM. And so if you're an operator and you're trying to understand how much fuel savings am I actually achieving, and you don't have that pilot ready time, you don't know what the actual gate hold was, and so you're left to guess as to what type of fuel savings. So that's one thing to keep in mind, that we are the precursor to TFDM, but we weren't forced to color inside the lines, as Al would say, on everything, and especially on some of these data products, we have data that might not be available in that official TFDM or TTP feeds.
That's a great point. So yeah, I mean, not everything that we've done you'll be able to replicate, once you're connected to the TFDM feed. But a lot of it will still be possible. So that's sort of, one thing we're trying to pass on in these reporting sessions is sort of our philosophy and our approach, and whether we can share the data or not, at least how we've thought about things and how we went about doing it. Because every organization is going to want to have some way to view this data, right? When they're getting SWAM, they're getting connected to more and more parts of that, and eventually the TFDM terminal publication, the TTP feed. That's an even richer data set, and what you're going to do with that. This is a way we've tackled it, and hopefully that provides some inspiration going forward, even if you can't replicate the whole thing, or you wouldn't be interested necessarily. So a little more detail about each of these modules. The basic descriptive data, I don't know that I need to read every line of this to you. But the idea here, this is sort of static descriptive data about the flight. Schedule and actual times, which resources did it actually use. Because we do have surveillance on the surface, we can see, we don't see which gate it uses, we get that data externally, but we do observe which spot it crosses, which is pretty useful for understanding the operation. Information about whether a flight was canceled or not. We do include canceled flights in our data set, and some flights are canceled and then uncanceled, and we try to capture that peculiarity as well. We capture some data about the routes, so as routes are refiled, we try to capture that information. Some new information we've added here is we now have some visibility into the operating carrier versus the marketing carrier, so the so-called major. We now are able to group that, which is super useful because some of these airports have significant, quote-unquote regional operations. You need to figure out, who is Republic flying for on that particular flight. You don't necessarily know, so we have some visibility into that now, fortunately. We track some things like, long on board or priority status, some information that's input through the ramp tools to be able to understand operator priorities with respect to flights. So basic descriptive data here, but it's a pretty rich data set, and the thing that to me that's really interesting is how it's all in one place, and we're not going to different tables, we're not going to different data sources, we're not trying to figure anything out. It's for one flight, you can go and look at the entire progression of that flight, sort of through our view of its life cycle. And these slides will be available, obviously, so everyone can go back and study them if they are so inclined. So banks, there's a lot of different ways to describe banks is the main thing I would say. Different user groups, different organizations may have a different idea of what a bank is, and that may depend on their job function or their analytical needs or any number of things. But the point is we want to recognize those different ways, and we want to be able to serve those different needs with the data that we're providing here. So one way to do it may just be static windows. And some partners may define banks that way. For example, from 1215 to 140, that's a bank. Really, and sometimes that's just treated as a bank no matter what else is going on, and that's still how we sort of look at it. That's how some people might look at a bank. So we want to make sure we're recognizing that and we're able to serve that need. But for some of the analysis purposes internally on the team, we want to be a little more adaptable to how conditions evolve each day. So we're trying to track sort of holistically how the schedule changes and how the operation is evolving each day. So we've developed a, I'll say machine learning, quote unquote, clustering algorithm to infer that bank structure from the operation that we observe. And we have different pieces of the different time elements that we can use to infer those banks. Because the scheduled bank is not necessarily, the scheduled pushback is not necessarily the same as the actual pushback if we're sort of clustering on that data, because the schedule and actual don't line up, right? So we use a density-based clustering algorithm. So some flights do not fall into a bank, which is sort of how the operation really evolves anyway, right? That at a strongly banked airport, there's a lull between banks, and you don't want to necessarily assign those flights to one of the banks. So we're trying to be cognizant of that. So we calculate these banks using the scheduled gate in, gate out times, actual takeoff and landing times, and actual pushback times. So trying to serve different analytical needs and different user groups. So that data is recorded on each flight, which bank it was associated, each of its milestones, which bank that was associated with. And generally those are consistent. If a flight pushes back in bank 3, it generally takes off as part of, quote unquote, bank 3. So we're trying to capture that. Visually, what does that look like when we roll it up? The colored bands there are the banks that we learned from the data, where the bars themselves are just the actual counts, in these smaller bins. So you can sort of, from an eye, you can sort of see, those look like reasonable banks, and that's what the algorithm is learning. So the point I'm just trying to make here is this is sort of machine learning in action. It's sort of a simple application of machine learning, but it brings a lot of value to the analysis efforts because we're able to adapt over time and say, bank 3 might have changed a little bit, but we're still interested in bank 3 over time and what that really looks like. And so that's part of the whole suite of the flight summary that runs every night. Okay, so ramp controller clearances. So the RTC tool, when it's being used, which is pretty consistent at Charlotte, records all ramp controller actions, and so we look at the times when different clearances were issued, which is the main thing that we're, from an analysis point of view, really interested in there. So you might end up with a typical clearance sequence like the ramp controller issues a gate pushback hold clearance, at the time, for example, the time there. And then about 4 minutes later may say gate pushback is now approved, so that corresponds to about a 4-minute gate hold. And then once they start pushing back and complete the engine start process, then they get issued a proceed to spot clearance. So we're capturing that data so we can look at the evolution of each flight, and we can sort of sum up clearances over time and see how the, sort of a measure of how busy the ramp is, if you will. Because in the ramp we don't have good surveillance data, but if we do have the clearances, we can see what's going on.
And this is an important point when you think about trying to model both the pushback process, the engine spool process, the ramp taxi process. If you don't have these data elements that tell you about the clearances, all you will have is an actual gate pushback, an actual spot crossing, and you'll be blind to kind of those processes that are happening in between the pushback and the spot crossing. Unless you have a team of people, standing in the ramp tower or on the concourse with stopwatches, which the NASA team has actually done to sort of calibrate some of these models. So this gives us tremendous visibility without having to go to that effort. We do capture other clearances that are used in the RTC tool. A generic hold, it's usually used for arrivals. Return to gate, so if departure taxis back to the gate, that one pops up erroneously sometimes. So we developed an algorithm for what does a true return to gate clearance sequence look like. Sometimes the controllers will tap that option accidentally. It's right next to one they use a lot. So we want to make sure that we're not overestimating the number of return to gates there were.
Clearance not set, that's sort of a fallback. Cleared to gate, for an arrival once it's crossed the spot to taxi to the gate. So we're looking at all these different things, and they'll all help us answer all sorts of different questions. And this is really unique, valuable data. Unfortunately, not going to be available necessarily from TFDM, but it's provided a lot of really good insights for the team and a lot of good analysis results that you'll feed into some of the presentations you'll see later. We look at last clearance type issued. That can indicate a flight that something strange happened with, and they stopped using RTC while they sort of dealt with that flight manually. We look at the pushback duration, as Jeremy said. We're able to estimate that. So this is really a rich data set, but because it is input by humans, there's noise, and we're trying to compensate for that. Flight states. So the internal model, as it's making predictions, it's modeling its estimate of what state the flight is in, and there's a long list of what those are there, and that's a sort of typical approach in these surface simulations or surface modeling systems, trying to understand where is this flight in its life cycle. So we get the times that those happen, so we can again look at the progression. That's maybe more of a diagnostic piece, but it's proved useful as we track down bugs. So surface metering analysis, obviously this is really key to the work that's been going on at Charlotte for years. We want to understand all kinds of different things about surface metering, and we want to do that in a standard way. So we've tried to roll that all together here. Some values, I'll say, I call it surface metering, but this is actually where we get the pilot ready time, because pilot ready time is really key to so much of surface metering. So we just say, sort of give me the pilot ready time for all the flights, and then get the surface metering data for those flights that were actually metered. So the pilot ready time or the flight ready time there, we sort of use those terms interchangeably. How we compute that, if we have the time that the clearance was issued, either gate pushback hold or gate pushback approved, we know the ramp controller has been in communication with the flight crew there, so we know that that's sort of then the flight crew saying we're ready to do something, and the controller saying we're giving you permission to do something or not. But if we don't get those, which does happen sometimes at Charlotte, if depending what's going on, or at DFW, we don't have that data, for example, or left field. So then we say, when do we first observe that flight on surveillance? We know the flight is obviously ready. It's sort of tautological, right? They must be ready if it's taxiing. So we're trying to roll this kind of information together and get our best estimate across all the flights, depending on what data are actually available. Accounting for return to gates. So if a flight returns to gate, do we want to think about the first time it called ready, or do we want to think about the time it called ready after it returned to the gate? So we're trying to make those decisions and have standard ways of handling the data. And capturing predictions. What were the control times in effect at that pilot ready time? What was the system predicting the flight was going to do? Was the system predicting the best thing the flight could do at that time? So other things about metering specifically that we build on top of that pilot ready time. What is the metering status of a flight? Which is not as trivial a question to answer as it seems. Was this flight actually subject to surface metering? Was a hold recommended for it? Did it actually hold? Actually answering those questions is pretty tricky. We have measures of compliance to the pushback time and the spot crossing time. So, again, sort of a trivial thing to compute, but we're trying to make sure the logic for that is standardized in how we handle seconds difference, for example. And the standardized windows that we use in the project. So gate holds, what was advised at pilot ready time, what was actually the actual hold. There's some metrics that are interesting to different user groups based on their incentives and their operational needs. Was a flight held beyond its scheduled time? Was a flight held beyond its L time? That's the sort of old school EOBT. We estimate fuel and emission savings associated with those gate holds. So that's when you see the benefit numbers being touted for ATD2. That's really where it's coming from. We have an engine that we use for estimating the value of those. What's the emissions and fuel for that time interval. So a lot of this data is also, besides going to the flight summary report, it's actually distributed to some of the user partners to maintain common situational awareness. They want to see this data throughout the day. And I know that they use it because as soon as it stops flowing, I get a ping and I need to figure out what's happened. So it's pretty neat to see them actually using it and relying on it for managing their day-to-day. Predictions at events. So obviously the system is making all kinds of predictions. That's how it's doing what it's doing, trying to predict what's going to happen and how best to respond to that. So at all kinds of events for the flight summary report, we want to say, what was predicted to happen when the flight pushed back? What was predicted to happen when the flight actually took off or landed? So I had a list of events there for each flight. For departures, for arrivals and departures, it's fairly straightforward stuff. Like I said, we measure some of this at pilot ready time, but also at actual pushback time, spot crossing time, queue entry time, takeoff, and then fixed crossing. We predict things like downstream in the life cycle. What spot is a flight going to cross? What runway is it going to use? And we measure that accuracy over time. And the system is remarkably accurate at predicting things like runways and fixes. It's pretty good at predicting spots. And gates, we get the data in advance, so we're pretty solid there understanding. So it's really neat to be able to track that performance. And it helps us identify problems, that if accuracy all of a sudden drops, we know where we need to start digging in and figuring out what has changed in our data feeds. For example, if the software itself hasn't changed. So we track those sources where those predictions are coming from, based on which part of the model or if it's coming in external prediction. Times that are predicted at the same way, as we predict resources, if you will, the spot on the runway. We also keep track of these different time predictions that are made at each of these events. A lot of acronyms on there. You see OBT, that's off block time. That's basically a pushback time, right? If you're not familiar. So the U there is unimpeded or undelayed. So it's, if a flight has no other constraints, what time do we think it would really push back? So all these different times we're sampling at these events as well. When the flight pushes back, what time does the system think it's going to cross the spot? What time does the system think it's going to take off? What time does the system want it to take off? So we can look at those. And same thing for arrivals. We have the same sort of progression, what's going to happen for the future events. And this is really useful for sort of debugging the scheduler, for tracking the accuracy of our predictions. There's a lot of questions that we've investigated using this data. All right, EOBTs or L times. This is the data provided by the operators. I don't know how many people are associated with operators here, but the data that's being generated internally there for their best estimate of when that flight is going to be ready to push back from the gate. That's really important data for the ATD-2 system as it tries to schedule these flights into the different downline resources. So having the accuracy there's several presentations later on about the importance of EOBT accuracy. So we're trying to track that, and this is sort of our first level of visibility to that, is what is the EOBT predicted at different events, but also before we get to certain events, how good is that EOBT? Prior to pilot ready time, 30 minutes say, when we're looking backwards, we can say how good was that EOBT, how good was that prediction with respect to pilot ready time? Because what the EOBT is really trying to capture is pilot ready time, right? Because during surface metering, the pushback time is not the same as the pilot ready time. But the pilot ready time is really what the EOBT is trying to predict, because that's when the flight is actually ready to push back. So, prior to that, how good is the accuracy? How good are these predictions? So we're able to look at that. We're able to understand how that changes over time. We see right away when carriers make algorithm changes. We can see it as it flows in, and the accuracy changes fairly starkly. We can see when it stops flowing. That impacts the system significantly because it does not have such a good visibility and sort of a dynamic visibility.
Do you have a recommendation for some of the airlines who are not quite up to speed yet on how to do that?
Let me repeat. Can I get you to ask the question in the microphone just behind you so that we have a recording of it?
There you go. Good morning. I'm with JetBlue. We haven't quite tackled this EOBT thing yet. Do you have a recommendation on how to calculate that? I know Tim Nisnik has done things and others have, but you got a recommendation coming down?
I mean, there's all kinds of different ways you could do it. I could dream up all kinds of things just depending on what data you have internally. There's things you could track. You know when the flight landed, right? Or you can make a prediction when it's going to land, and you know what it's supposed to turn around as. So you can make some predictions there based on your internal systems that you probably already have, right? And it's sort of expanding the logic used for LTIME, if you will. But then internally when you start loading baggage, we start loading passengers, when the flight crew is doing their checks, right? If you can roll that data in, it's not trivial to capture all that in one place, I'm sure, and to turn that into a prediction of, based on we started loading now, we're going to be ready to push back in 27 minutes or whatever it is. But I think that's sort of the general thought process, is trying to capture those events.
And I think, luckily, as you said, we have Tim in the audience here, who is, I would say, at the forefront of the EOBT models. And I think he's a great resource. He's been very open in the past with other airlines and operators. I even think they might have published a paper on it as well, so that my recommendation would be to talk to Tim.
Been there, done that. Could you tell me how bad, per your report, our L times are?
We do have that data. That's an Al question if we can share the accuracy there. But yeah, I mean, that's certainly, we know.
It's a good question too. So as Joe's specific question was about how do we as an airline operator evolve and create the EOBT, and that's not the focus of this discussion today, but the focus of this discussion today is how do we measure it? All right, so if we don't have an objective measure of quality of this, then how are we going to know if we're doing better or worse? And it's a non-trivial problem. And so what we'll talk about here is measurements of EOBT accuracy and L time, and that in and of itself is a very complex subject. We do have some of those metrics to Andrew's point there. We don't give out any airline-specific metrics, obviously, but we do have some general data that I think we could share across that. And the good news is, for the folks that are really lining up and trying to improve their EOBTs over L time, we're seeing, I would ballpark it at a 50% reduction in uncertainty. So I mean, it's just stellar if you think about what you can do with the better input of data into the rest of your system. And the L times, keep in mind, we're better than P time. So we have this scheduled time, then we have the L time, which was a progression beyond that. EOBT is a progression beyond that.
Yeah, I mean, qualitatively, we don't have to build your internal business case, right? But from our perspective, the organizations that are investing are definitely getting more accurate. I mean, and that's the benefit we're really looking for on this side. So yeah, EOBT is super important part of our data.
In some of the later talks, we'll even show some of the operational efficiencies of those improved EOBTs, whether it be scheduling into the overhead stream or those benefits achieved from surface metering. So they're really important, not just for one aspect of flight. They actually span many different kind of aspects, which I think is something important to keep in mind. It's not just one thing that it's used for.
Okay, next block of stuff we look at here, TMI impacts. So we've put a lot of effort into capturing control times in the system and making sure we're getting the right control times and updating them when they're actually being updated in the FAA automation. So, EDCTs associated with ground delay programs, we're capturing those at different events throughout the flight's life cycle, when those are coming in and what the actual time value is, how many times it's being updated. We measure compliance there as well. We have great visibility into that. With the Fuse data, we have great visibility into how compliant flights actually are with respect to those, which is a neat thing to be able to see and to look at how that varies over different sort of operator categories, but also different flight categories based on having multiple controls or participating in service metering and how what the interplay there with EDCT is. Ground stops, we track data with respect to those. MITs and fixed closures, we track the values that are associated with those MITs. How far was that spacing supposed to be? How many times is that restriction updated? What fix is even included here? Was there an alternate specified? So things like that on a flight level. And as I said, in the after lunch session, we're going to talk about from the program level, what are we able to extract and look at, which is some neat data that I haven't actually seen elsewhere that we're now capturing. So. APREX, so that's another sort of TMI. This is the scheduling into the overhead stream. That's such an important part of the concept, APREC, or call for release. So we're capturing, as with service metering, we have a suite of metrics that we're interested in here in terms of how the flight was scheduled, when the flight was scheduled, how much delay was assigned, quote unquote delay, how much delay was assigned by TBFM for that takeoff time. Where was the flight in its life cycle in our internal state? Was the flight still at the gate when that APREC was scheduled, or was the flight taxiing when there was an update made because suddenly the flight crew thought they could be at the runway sooner and they're trying to get a new slot? How often is that rescheduling happening? We have this concept of pre-scheduling. If you're not familiar with that, basically it's using the EOBT that's provided by the operator to request a slot in the overhead stream ahead of time before the flight actually sort of calls ready. So prior to the EOBT, the system automatically will request a slot going into Atlanta and O'Hare now. So we're trying to look at, that makes the EOBT really important. The flight better be ready because it's got a time already scheduled at the runway it needs to meet. Another case of how the EOBT is used. APREC release mode, TBFM is a mysterious beast, but there's a lot of different ways that it can be configured. And we try to capture that because it helps answer a lot of questions in terms of the efficiency of the system as it impacts ATD2. So, in terms of like automatic scheduling or semi-automatic and all these things. So from the rescheduling, we do estimate some benefits associated with that. When flights can get earlier times, they're not sitting on the ground, burning fuel. So we do measure those benefits when the flights are able to be shifted earlier or later. Compliance, again, I keep coming back to compliance and say, it's more complicated than it seems. One way it's more complicated is, what resolution of the times we use. Do you look at seconds or not seconds? Do you truncate that? And where do those windows, where are they relative to? So we've tried to incorporate all this data in one place. This is another place where the data is distributed to users at some of the FAA centers. This gives them pretty good visibility into what's going on with the APRECs coming out of Charlotte every morning. And they use this data and it helps them understand what they did the prior day and what they could do better. So it's neat to see that happening. Taxi times, obviously key for surface metering and for TOS operations in terms of being able to predict when a flight's going to be at the runway. We need to be able to make a pretty good prediction of that taxi time. Obviously we're dependent on the pushback time and our prediction of that, but we need to also have a good idea when it's really going to get there once it does leave. So we record predictions made by the system for these undelayed taxi times. It's sort of this notion of, flight was unimpeded, how long would it take to get there, but given some of the constraints we have, how long does it take, and then how long does it actually take? And we're able to break that down between the ramp and the movement area, which is neat because we do have that, we're able to observe that spot crossing event. Even though we don't have great surveillance in the ramp area, we still get that pushback time and the spot crossing time to infer the ramp taxi time. We have standard logic for what is a bad value, just because some errors do creep in there. So we've tried to incorporate that, based on our learning over time. What does a bad value look like? Obviously, a 0-second taxi time isn't right. But probably a 3-hour taxi time isn't right in the absence of no weather constraints or other problems, right? So we're trying to roll that logic in. Actual taxi time, as I said. So then the excess taxi time, which is a really important metric for our scheduling engine. Keep track of that for each of these phases of the operation on the surface. Gate conflicts, this is an issue that came up several times. It's obvious, it's always a huge question. It's always the zinger or the gotcha that people raise. Tim?
Just go back one slide. So a taxi, you mentioned undelayed and actual, but aren't you predicting estimated taxi at certain events as well?
So Tim asked, that we're capturing actual and undelayed taxi times, and asked if we're also capturing predictions of our taxi time. So we capture the TTOT at discrete events, which will give you that predicted taxi time. And so at pushback, spot crossing, queue entry, we capture the target takeoff time.
Okay, so you can infer the predicted taxi time.
Right, and our notion of undelayed isn't sort of 0th percentile. We have built in some logic. Hanbong has done a tremendous amount of work trying to figure that out. What does it really mean, for different phases of the flight even? It's a really complex, that's a whole presentation in itself, so. Gate conflicts, right, this is the one that everybody comes back to and say, oh, surface metering isn't gonna work because of the gate conflicts. Well, we actually model and record data on gate conflicts that do occur during surface metering, and we're able to look then at the relationship between number of gate conflicts and sort of application and efficiency of surface metering. So we capture things, both the arrival, the incoming flight, as well as the flight that's the departure that's still blocking the gate. We try to look at both of those and see, when was a prediction of a gate conflict made, at different flight milestones, was there a gate conflict predicted? How long is a gate conflict predicted to be? The system is able to predict gate conflicts down to the resolution of 1 second. I don't think anyone is really worried about a 1-second gate conflict that's being predicted. The ramp controllers are sort of managing that internally. They're experts at that. But we've got several minutes of gate conflict predicted, 10 minutes, 15 minutes. That's really when there starts to be a concern, and then they're going to deal with that. So we're able to look at, what was that prediction when a flight landed or when it crossed the fix, for example, and the arrival's coming in. Is there somebody still blocking that gate? So we have a lot of visibility into that based on the modeling that's going on in the back end. And from the flight summary perspective, we try to roll that in and summarize, what did that progression of the gate conflict look like from the arrival's point of view, as well as the departure that was trying to leave. Is some other flight coming to try to take my gate right now? So, we use that to look at the relationship between service metering and gate conflicts.
Sorry, Andy.
Yes.
Just a question on this. What are you using that? How are you presenting that to the user in real time?
So the question was, how do we use or present the gate conflict data to the users in real time?
So yeah, there are 2 sessions, maybe tomorrow afternoon, about the RTC tool itself and some demos of the RTC tool. So the RTC is the ramp controller is an interface that they have to the ATD-2 system, and they actually have all kinds of alerts on there that they flag and color flights based on what the prediction is about that kind of stuff.
Yeah, and the users are allowed to select different parameters, like I want to be alerted to a gate conflict 10 minutes prior to actual on, or 15 minutes or 0 minutes, and so those ramp controllers can kind of adjust the system to what they feel works best for them.
Yeah, so they can apply their expertise, because they're really the pros in resolving those and figuring out if it's a concern or not.
So on your ATD2 display right now, if there is a gate conflict, you change the color to orange, red, whatever, right?
I don't know the color. Cynthia's the expert,
magenta.
but yeah.
Right, exactly. So if a controller sees that, are they automatically assuming that there is an actual gate conflict and they won't taxi the flight to the gate and then skip over the stop?
Well, I mean, I think they're supposed to assume that is going to happen. Like if they take no action and everything sort of plays out as it's predicted to right now, that there will be a gate conflict. That when that arrival, taxis up to the alleyway, there's going to still be a departure sitting there, and so the idea is that they're getting this advisory, so they resolve it before it gets to that sort of blocking situation.
And so the question was kind of, how are the controllers managing the gate conflicts when they get that information? And I think some of the philosophy here is that the operators are in control of the ramp, and that we would like to inform the operators that we think a gate conflict is happening, how they resolve the gate conflict, if they want to get that departure off the gate and hold it in the ramp somewhere else to get that arrival on the gate, if they want to hold the arrival off the gate, that's their decision. We just provide the data and the information to inform them so they can make the best decisions.
But the ground control themselves simply taxiing into the gate on list code otherwise?
So that would be, I think, more of a local kind of agreement between the FAA and the ramp. So at Charlotte, they have a very highly collaborative kind of relationship between ramp and the FAA. Same with the DFW, where when the arrivals come in, if there is a really big gate conflict, they'll agree to hold it out in the active movement area as opposed into the ramp, that incoming arrival. So those, I think, are things like when we go back to the morning talk, and Carol likes to say, you see one airport, you've seen one airport. I think how they handle those gate conflicts when kind of when they actually kind of manifest themselves are different depending on the airport or the situation that's happening. But the main idea is just to give them the information to allow them to make good decisions.
And then to be able to do analysis after the fact and say, did that, whatever strategy they're using, are we still able to surface meter in the face of these gate conflicts, things like that?
Is it recorded like when it's clear, when there's no conflict anymore? Yeah.
Right. Yes. So the question was, do we track when the gate conflict was clear? And yeah, we do. We're able to infer that from looking at the 2 flights.
Tools on the ramp side and on the STBO, it clears once it.
Tomorrow afternoon at the 1:45 session, ramp traffic console, that's one of the operational use cases that they discussed in that session.
We had a question back here.
Yeah, sorry, I was just wondering if you're using the intent to hold in the movement area or ramp area as part of these calculations.
So the question was, are we leveraging the intent to hold as part of these calculations? And for ATD2 system right now, we're not leveraging the intent to hold for to help those predictions.
Not a lot of holding space at Charlotte anyway, so, but, yeah.
Was there another question in the back?
Back there?
Yes, I'm from BREAKOUT, and I think just to maybe tell you what the airport uses that information.
Can we get you just on the mic so that we have a recording of this? Thank you very much.
So for example, am I clear?
Yep.
Yeah, so for example, when you have an arrival and you're predicting it to take between 12 to 15 minutes to get on to get up to a gate, what that information we use for is we tell the customers on that plane that it's going to take about this amount of time for you to get to a gate, so that the customers who are on that plane can make decisions. If that's their destination, maybe there's not much they can do. But if they are transitioning to another plane to go somewhere else, they can plan themselves ahead of time. If, let's say, they need to take lunch, they know they have an hour. But if, let's say, they have 15 minutes to get to the next gate, they can start making arrangements with the next flight. They can text, call, and tell them I'm on this flight. It might take me this amount of time to get there. Also, from the airline perspective, if they know they have a plane that is coming in, it's going to be late by 15 minutes, but they have about 20% of customers on that flight that need to get onto this other plane. So they can delay this other plane because they have a significant amount of customers coming from one plane that will be transitioning to the next plane. And the next step where DFW wants to take that from, you can see on the tier, now you have the expected times you're going to take on your TSA lines. Our goal is to make sure that when you are being told, we're gonna arrive at DFW in 15 minutes, you are also told the expected amount of time it will take for you to get to the gate. And NASA is helping us to get that information to make those predictions.
Thanks, that's a great example.
Yeah, thank you very much for those insights.
All right, other section, I've just got a bucket of other data here because there's other things that we've started collecting in the flight summary file based on specific research questions we had or user needs. One thing that we've collected that turned out to be much more complex than I expected, at least, and maybe I was naive, but the whole concept of what a pushback time actually is and how we represent that in our data and how the system uses it is a really complicated question. We can get those pushback times, AOBT, from the controller inputs, when we see the gate pushback approved message if RTC is being used. Airlines, have their own measure of that, and they might have multiple systems, multiple automation systems that are generating those. For example, the safe gate laser situation is used a lot of airports, but also, parking brake is used sometimes. There's different measures of that come from an airline, sometimes multiple measures. Surveillance, we may have surveillance back to the gate, so we might be able to observe that actual pushback event, which is a difficult question in itself because the surveillance signal is noisy. We may observe the flight, 100 feet off the gate, and then we know it's pushed back. So there's a lot of different ALBTs, and we've spent a lot of time on the project mulling these over, figuring out the complications of each of these and how to use them, because that pushback event is a really important trigger in the system, particularly at Charlotte, as well as at DFW now, in terms of understanding when that flight is actually moving, because up until that point, everything is a prediction. Once we know it's pushed back, we have a much firmer anchor on which to make our downline predictions. So it's a really important question. This has given us good visibility, sort of putting all these different data sources into one place.
Do you get SIPS data for Charlotte?
We do. We don't leverage it though. So yeah, that's through the FAA studs feed, there's the surface movement event indicators that come through. It's a sort of parallel stream to the surveillance that comes with ASDX that the FAA systems are inferring these times as well, and we're not using those right now. But yeah, that's whole other source that might be a slightly, another 30-second difference that, confuses us even further. Airport configuration, so something else, as I said, we're tracking that at different flight events. We want to know, which direction was the airport operating in, or which runways are being used for takeoff and runway, for runway landing and takeoff. There's different, again, one airport is one airport. There's different ways they operate in terms of these scenarios for arrivals or departures and how they're using the fixes, and we want to be able to look at performance, differential across those scenarios. So we're trying to track, how is a flight operating? Does for example, if the scenario or the configuration changes partway through the flight's life cycle, that has a big impact on, what performance we would expect from that flight. So we're trying to be able to get some visibility into that. Other data, again, downline times for departures. This is one little section in here, but there's a whole presentation on it later about, is surface metering causing any impacts on, arrival performance at the downline airports? It's not, that's the short version, but, we need to have a way to gather that data and collect it and be able to have common visibility into it. On-time performance writ large, at the local facility here, we're tracking the standard, D0, D15, A0, A14, A15, however you want to call it. So we can look at that in sort of the DOT standard way. Again, these are just, you could just look at it as a difference of times. But it turns out it's more complicated than that because the airline's schedule times you're comparing against are only to the resolution of seconds. So if we then use our times, the airline times are resolution of minutes. If we use our times at a resolution of seconds, we're not going to be scoring every flight the same. So if a flight's 15 minutes and 5 seconds late, we're going to treat that as late. But if we truncate that actual time to minutes, then we're looking at a difference of 15 minutes, and it's a whole different ballgame. So we try to match that logic as the sort of standard DOT logic based on the times that they have. So we're able to look at that in a common way. So we compare against external data sources to be able to develop that approach. More other data, integrating with the electronic flight strip system was a major undertaking on the back end. So we want to make sure that we're able to have some visibility into how it's being used, what data is being input there that's flowing to ATD2. So different events that are captured on that flight strip, we are also capturing in the flight summary report. We're able to look at those on a flight-by-flight basis and roll things up that way. First surveillance, this is a big question of when do we first start observing that flight. It varies by airport, by gate, by terminal at the airport, even by, over time as they install new sensors or sensors go offline, trying to understand what's happening there and where in that flight's life cycle is it when we first start observing the surveillance. Which has helped us answer an important question. I'll give an example of how we use that data. Charlotte opened the A North concourse not that long ago, maybe 6 months or something. And we were getting flights that, some strange effects in the system. And we were able to go in and diagnose right away and say, we're getting surveillance on those flights, an hour before they're actually ready, before they're scheduled to push back. We know that airlines are not generally pushing back their flights an hour before they're scheduled to. That's just not something that's done, right? So given that visibility, we immediately know where to dig in and say, why are we getting surveillance in these flights so early? And then it turns out just the sort of geometry of the airport and where the sensors are located, that if the transponder was already on, we were getting ASDX surveillance on it, and the system was sort of triggering that as a pushback event, which led to all kinds of downline consequences in the back end. But having this data, we were able to target where to dig in right away. So it was really useful.
So that's ADSB transponder data?
Well, we're not using the ADSB data directly, but if they're providing ADSB source data through ASDX, that's filtering down to us, yeah, because we do get the Cat 10 and Cat 11 both. So, okay. And TOS-related data, so this is our newest module. I have a whole section this afternoon on what we're looking at TOSes across all the different route options for each flight. But for a flight itself, there are some sort of flight-specific things across all of its route options when we sort of aggregate in that way to support some of our analysis for phase 3 here. I apologize if you're not familiar with the acronym TOS or the concept here. The idea is basically that they're, airlines can have some options to escape the terminal area basically and can trade off, which route they want to take rather than just what they filed. And there's a whole process that's been implemented to do that. But we're tracking things like when does a flight become eligible to participate in the TOS system? When was it submitted? When was it approved by the controllers? We have a more robust, sort of broader scale terminal scheduling engine, so we're capturing predictions and plans from that at different flight events as we do the other predictions we're making from the sort of surface metering focused engine. We have the notion of what's the best TOS route, based on the data that we have and the assumptions that we've made in the system. We think this would be the best route for that flight to take, and we can track that at different flight events, and then you can compare that to what the airlines actually did. And see how our logic compares or how good we think their decision-making process is on that. Terminal transit times, so as we have taxi times on the surface, we also have transit times through the terminal area, and we have different predictions of those and measures of actual and different ways to get them. So we're trying to capture all that data in one place so we can see for a flight what prediction was actually used and how did it perform in comparison to that. So this is all at a flight level. As I said, we'll talk about at a more granular level later. For each flight, there's multiple route options, and then for that sort of file, we track what are the data associated with each of those route options for each flight. So quickly, here's some reports that are built on top of this core data file. I already mentioned the APREC compliance report and the post-bank gate hold report. So those are summaries of those specific performance characteristics that go out that are used by operational personnel every day. We have a daily data digest that has some internal and external users that summarizes the whole day's operation in a variety of dimensions, just in terms of flight counts and banks and delays and EOBT accuracy and number of control times and TMI impacts, covering all 3 of our airports, trying to respond to the unique needs and unique characteristics of each airport. So we've put a lot of effort into developing that on top of this, these core data artifacts. Sure. Sure. We could talk about that. So the question is about if you're on the daily data digest, not all of it is necessarily clear. And the documentation, as Al said, is something we try to do the minimum level, but sometimes we're not even there yet. So we could talk about that. System prediction quality, we're constantly tracking all kinds of performance metrics, how good are our predictions for times and resources. And there's more. There's more on top of this that we do that we can talk about offline if you're interested. So just to wrap up, this was about the flight summary report. It's this tabular view we generate for a day, 1 row per flight, all sorts of different metrics describing the life cycle of that flight, the predictions that were made, and its actual performance. It's a starting point for a lot of the analysis that we do, trying to reduce the redundant work being done by analysts and eliminate or reduce the possibility of different people taking different approaches leading to contradictory results, trying to have sort of a common view of things. Actually, Al, in his copious spare time, wrote the first version of this. So this was really Al's idea, really driven by him, and it was really a great thing for us to focus on because it really has been very valuable for the project. It's highly collaborative across the team and with our users as people ask for new visibility, new data, whether we're able to roll that in. As I said earlier, it's sort of a generic technical approach. It can be adapted as appropriate based on what data is available in the future through the TTP feed and your own internal systems and what your own interests are. But the one point I will make is it was a lot easier starting with the fuse data. So whatever notion of a fuser you have for joined data streams, it makes it a lot easier if you have a common identifier at least to sort of join on, right? So this is our approach. We think that it's working pretty well for us. Whatever approach you take in the future, though, the main takeaway I would say is that it's really good to have a sort of 360 view of a flight and be able to look in one place and say, here's what this flight did. Here's what we know about this flight, and have a way to a common terminology there. So we have 7 minutes till the lunch break. There's already been some good questions and discussion, but we have time for more.
Yeah, so I have some of these questions on the conference IO that we can go through, and then if there's any remaining time, feel free to ask any last questions you guys have. And if you see us in the hallways and you have anything else, just kind of feel free to grab our ear and ask away. So the first question here, what is L time? I'm not familiar with the term. So the L time, the acronym is LGTD, the latest gate time of departure, and that's a CDM data element that was supposed to replace the scheduled off-block time, and it's just supposed to be a slightly kind of more accurate view of when that aircraft will be available to push back from the gate. It's somewhere in between, as Al had mentioned, the scheduled off-block time, which is static and doesn't change, and the EOBT, which is more dynamic and trying to evolve with the situation as it evolves on the surface. So I would say the L time is maybe somewhere in between the scheduled off-block time, and the EOBT, the earliest off-block time.
Where did you say that reference was defined in use documentation?
The surface CDM ConOps, I believe. Is that correct?
I think LTime even precedes SCDM ConOps, but LTime is it's a concept. I think it emerged in the
TFNS.
Yeah, TMFMS
Okay.
data element that came out of the whole CDM process when that first started in terms of airlines being able to provide an estimate of when the flight's going to be ready more dynamically than the schedule time.
Okay. So next question. What in these reports is internal for NASA development analysis purposes, and how much goes back out over SWIM? And so what I would say is that we definitely have, internal data, which is what we mentioned. We have data that won't actually exist in the future TFDM system. But NASA is in this unique position where we're both a consumer and a producer of SWIM data. So we actually have a prototype of the future TFDM TTP feed, the TFDM terminal publication feed. And as we had mentioned, sometimes we color outside the lines. For that TTP feed, that prototype feed, we gave the exact specifications of what will be in the future TFDM system so that operators are able to connect to our research feed and to start to interact with the TTP and get prepared for the future rollout of TFDM.
Yeah, I mean, so what we're, the view we have here, I guess, is sort of a parallel stream, from what we're pushing out over TTP, that this is our way to roll up the data for analysis purposes versus the TTP, which is just more of a feed. Although a lot of the same data exists there that exist here, they're being pushed out. There's sort of different paths, if you will.
Next question. So is the Fuser data available to external consumers? What kind of SLA exists for its long-term support? So one thing I would say in terms of long-term support is NASA ATD-2 ends in September 2020. And so there's not a lot of support beyond September 2020. So we are trying to set up a Fuser in the cloud prototype, and we're trying to envision what the follow-on work to ATD2 would look like. And, we think that it has a lot in common with some of the things that are discussed specifically in this analysis track here. But I would say, and my branch chief is here, so I don't want to speak out of turn, but I would say that we're kind of still in the formulation process of what is happening after September 2020. So I can't give any firm kind of guidance on that at this point.
And there is a session here about this Fuser in the cloud concept, that there's a prototype out there, and I think there are some users connected to it trying to consume data, that it's a parallel implementation, if you will, for the data backend that exists for ATD2 to try to provide data out for here's what our idea of fused data look like.
And yeah, so what Andrew showed here, this flight summary, we generate these products specifically for flights that are operating at Charlotte or DFW or Dallas Love. However, that Fuser in the cloud is actually, I believe, a nationwide.
Yeah, right now I think they've got it running nationwide with TBFM and TFMS data, fusing that. So, generating a common ID, if you will, and putting it into a common data schema.
Is the algorithm available, or is
there is a lot of, so I think they're trying to figure that out, how or if or what to share in terms of code, but there's a considerable amount of documentation that has been published about the fusion logic.
Yeah, so go ahead, Cynthia.
Well, I was just going to say the Fuser in the cloud presentation is going on right now, but do remember that all the notes will be posted online afterwards, and so I would recommend that you go read that presentation afterwards, or I can introduce you to the fellow that is the main architect of it.
Yeah, and I believe videos will be made available of all these talks. So if you were here and you really want to see what was going on in the parallel session Fuser in the cloud, those videos will be available. I think our position is that we think this data is this data is very valuable to the operators and to the community, and so we're trying to find any way possible that we could provide this data to the operators, to the community, so that they can make better decisions with this data. So I think it's our goal to get this out to you guys. We're not kind of sitting on this thinking this is our proprietary product. We are trying to, that's somewhat of the purpose of this whole kind of industry workshop, is we want to share with everybody what we've learned over the last couple of years. Okay, so we have 1 more minute here. Let's see. So one question, so how are departure queue times calculated? So departure queue times, well, they're always benchmarked against what we call the unimpeded taxi time. So prior to an aircraft actually taking off, we will have a predicted, what we call the target takeoff time, TTOT. And so we can compare the target takeoff time to what we call the unimpeded takeoff time, the UTOT, and the difference between the target takeoff time and the unimpeded takeoff time is our estimate of the queue. And so that's in this predictive world. But then after the fact, we have an actual taxi time. And again, we have what we think is an unimpeded taxi time. And so we then take the actual taxi time and subtract the unimpeded taxi time and get what we would call the actual kind of time in queue.
Well, I'm not sure who put the question in. Then maybe they didn't want to raise their hand. But the question may have also been, how do we decide when a flight has actually entered the queue physically? And in that case, we have a geometric approach that we've used. We've tested trying an algorithm where you sort of infer if the flight in front of me is stopped and near the queue, then I am also in the, and I stopped, then I'm also in the queue. We've tried that. It was very difficult to get to work right. So we've adopted a geometric approach where for each runway at each airport, we have a box. And it says once you enter that box, you're in the queue. So if the queue got really long, we're not going to capture accurately when the flight enters the queue. If the queue is really short, we're going to overestimate taxi time by some number of seconds when the flight sort of taxis over that entry line and then eventually stops sort of deeper into the queue. So it's an approximation.
Yep, and so we're essentially coming up to the end. I have two more questions I'll just try quickly to answer that are on here. First one, are you using the APREC data to look at the buffers applied by ATC when requesting a TBFM departure time? So shameless plug, this afternoon I'll be showing the APREC data, and that is one of the things that we have data and graphs for that we'll actually talk about. So please join us this afternoon. And then last one, it seems like most all flight summary reports are generated from departure perspective. Can you also generate them from an arrival perspective? That we are already doing that. So Andrew here has laid out this flight summary where each row is a unique flight. One of the columns is departure, is arrival. And so we're capturing both the departures from Charlotte and the arrivals into Charlotte. And then, we try our best to stitch in this holistic view of, the whole picture, like those arrivals into Charlotte might be metered by TBFM, things like that. So we're trying to stitch together that holistic picture because, this is one thing we like to say here on ATD2 is ATD2 is the name of the project, but really the name of the system is IADS, Integrated Arrival Departure Surface. You can't just think about this problem in one single kind of domain, i.e. arrival or departure or surface. You have to look at the integrated picture to really kind of come up with a good solution. So
yeah, my apologies if that was the understanding. No, we do have data on arrivals. I just talk about departures more because they're maybe a stronger focus, at least at Charlotte, so there's sort of more data elements. But yeah, we capture all the same parallel sorts of events for arrivals as well.
And so we're over our time, but if anybody has any remaining questions, I think we're more than happy to answer them. If not, we can head off to lunch. So I'd like to thank everybody for joining us today, and we'll have some more good sessions this afternoon.
All right.